The fig cookie is one of life's sweet mysteries. Who hasn't wondered how they get the figs in that seamless pastry wrap? It turns out that the automated system for producing fig cookies actually dates back to 1891, and it's what makes the fig cookie a snacking success. Fig cookies are a modern way of packaging a fruit which has been consumed for millennia. Making the fig cookies pastry wrap begins with bags of sugar, which they empty into a big mixer. A couple of buckets of corn syrup follow. Then they add an emulsifier called lecithin and some vanilla flavoring. The bowl tilts up for a quick mixing. A worker adds organic bread flour and leavening ingredients to the mix. They reactivate the mixer, which blends everything into a thick, sticky batter. Once properly mixed, they transfer the batter into a large holding tank. Meanwhile, they prepare the fig filling. A worker loads big blocks of figs into a mixer, then adds a generous amount of crumbled cookies for texture and flavor. They mix the two ingredients, then pour in corn syrup to add moisture and sweetness. They add some salt and give the batch another quick mix. They sweeten the fig mix some more by adding plenty of sugar. And now the jam for the center of the fig cookie is complete. The fig jam and the pastry are now positioned for a merger. It will be a neat trick, and a special piece of equipment makes it possible. It's essentially a funnel within a funnel. Rollers press the jam through the inner funnel while pushing the pastry through the outer one, encasing the fig filling in a seamless pastry jacket. Here's the process in action. The system generates long rows of fig-filled dough. And that's how they get the fig jam in the pastry. Next, a technician carves through the dough and removes a few uncooked fig cookies. It's time for a quick weigh-in. This confirms that this batch of fig cookies will be exactly the right size. Now it's into an oven that's longer than a bowling alley. It bakes and browns the fig-filled ribbons of dough. Here, a roller compresses the baked cookies, so they'll fit into packages later. An ultrasonic frequency makes this blade vibrate for a clean cut, as it carves the rows of fig-filled pastry into cookies. The fig cookies are still a bit warm from baking, so they now chill out on a trip through a freezer. This cool down avoids condensation problems after packaging, preventing mold growth. The trip through the freezer also firms up the fig cookies, so they're less likely to crumble during handling. As she packs them, this worker examines each fig cookie for imperfections, and there's not one reject in the lot. The next step is packaging, where a machine parcels up the snacks. It moves trays full of fig cookies into a sleeve of metallic film. Finally, rotating jaws heat seal the package at both ends. It's taken about an hour to make this package of fig bars. And it's about time for a snack break. If the crowd is hungry, the whole package could be gone in minutes. But that's the way the cookie crumbles. Whether you work in a sprawling corporate office or in a home office, filing cabinets are an essential component of an efficient workplace. They keep your paperwork tidy, organized, and out of sight, yet just a drawer away. And when you're short on space, they make a handy counter for the coffee maker. Filing cabinets begin as sheets of cold roll steel, a thin type of metal that's easy to bend, weld, and paint. As the sheet comes off the roll, it goes through a straightening machine that removes the curve, then into a press whose dies punch out the shape of the specific part, complete with holes, slots, and embossments. A filing cabinet is made up of over 60 steel parts. For the top-selling models, the factory has dies specially designed to punch out each part. But that's too costly a system for models that aren't mass-produced. To make low-volume or custom-made filing cabinets, the factory uses this computer-controlled punching machine. This equipment operates at a far slower speed than the presses we just saw. But the advantage is that it can be programmed to punch out any size, shape, or design, no matter how complex. Several filing cabinet parts are designed to be bent into shape. Workers do that manually using a machine called a press brake. This particular part will become the top of the filing cabinet, so they're making downward folds along the perimeter to create 1.5-inch wide edges with strong and tight corner seams. This machine is called a dedicated bender because it only bends one type of part, the filing cabinet doors. The factory produces doors in such high volume that it pays to design a special machine to shape them. The doors are also bent downward along the perimeter to create edges 1/2 inch wide with tight corner seams. The cabinet's base is welded from the same type of steel sheeting as the other parts. Small steel reinforcements make it rigid enough to support the excessive weight of file-filled drawers. To join the cabinet's side and back, robots perform what's called resistance welding, fusing metal using heat from an electric current. The next set of robots welds the side and back unit to the cabinet top. After this, workers attach the base using what's called MIG welding, welding that adds extra metal along the joint to create a strong seam. Once again, it doesn't pay to invest in robotic welding equipment for models that aren't mass-produced. They manually weld low-volume items such as those small filing cabinets that roll under desks. In the paint department, rotary atomizers envelop the filing cabinets in a mist of paint that contains a synthetic resin for durability. These atomizers lace the paint particles with a negative electric charge. This draws the particles to a positive charge on the cabinets, creating a thorough and even coat. After 20 minutes in an oven to bake the paint, assembly can begin. Ball bearing sliders on which the drawers will sit, tracks for the fold-down doors, and door stops so the doors can't be pulled off their tracks. There's also a locking system that simultaneously bolts both sides of each door, making the files inside inaccessible. The last step is to install the doors and drawers using a rubber mount so as not to damage the finish. Each drawer can support up to 200 pounds of files. An interlock system lets you open only one drawer at a time. This prevents the cabinet from toppling forward.
The first fire extinguisher on record was built in Europe in the Middle Ages. It worked like a giant syringe that squirted water at a fire. The modern extinguisher uses compressed air as a propellant and douses the fire with flame-retardant liquid, powder, or foam. Squeezing the lever opens a valve that releases compressed air. The pressure then propels the chemical through the hose and out the nozzle. Production of the release valve starts with cylindrical pieces of aluminum called blanks. A carousel runs each one through 16 different machining stations. At each stop, under a shower of lubricant, tools shape the blank for 6.5 seconds. As each blank completes the circuit, it comes off the carousel. From blank to valve in 1.25 minutes. Now, the fire extinguisher's aluminum handle is riveted onto the valve. It pivots on a pin. Next, an aluminum lever is riveted onto the handle. This is the lever you squeeze to use the fire extinguisher. Then comes the valve stem, the valve's inner workings. Workers simply place it inside, and an automated assembly machine does the rest. It positions a spring over the stem to create resistance when you squeeze the lever. Then comes a retainer to hold both the stem and spring in position. Now, workers slip on a plastic thimble to position the rubber O-ring that goes on next. The O-ring acts as a seal between the valve and cylinder so nothing leaks out. The siphon tube runs from the valve down into the cylinder. The firefighting chemical goes up this tube, then out the nozzle. The compressed air inside the cylinder is what propels the chemical. This gauge shows if there's sufficient pressure for that to happen. After coating the gauge's threaded stem with sealant to prevent leaks, a worker screws it onto the valve. The valve unit is now fully assembled, tested, and ready for installation on top of the cylinder. To attach it, the cylinder needs a threaded collar. With the help of a press, a worker positions it. The cylinder also needs a bottom. The technique this factory uses to fuse the bottom and collar is called brazing. It's similar to soldering, but with a copper ring as a bonding metal. After positioning a brazing ring at the base of the open cylinder, a steel bottom is pressed into place. Then, workers position a brazing ring over the collar. Now, into a brazing furnace for 1 hour and 45 minutes. The 2,000-degree heat melts the 2 copper rings, bonding the parts they connect. Next stop, the static paint booth, where workers apply a positive electrical charge to the paint particles and a negative charge to the cylinders. This draws the paint onto the surface evenly. Then, it's into an oven for 45 minutes to bake the paint. Once the cylinders cool, automated machinery fills them with a fire-extinguishing powder. The main ingredient is a form of ammonia. When it's sprayed on a fire, the heat melts the particles of powder, fusing them into an oxygen-blocking blanket that smothers the flames. After the cylinders are filled, an automated machine screws a valve onto the collar of each one. Now it's time to pressurize the cylinder. The lever is squeezed to open the valve, enabling a compressor to fill the cylinder with air. They keep filling until the air pressure reaches 13 bars, about 6 times the pressure in a car tire. Next, workers screw on the nozzle and install a locking pin. This immobilizes the lever so the extinguisher can't discharge accidentally. As the instruction sticker says, in case of fire, you just pull the pin, aim, and spray. This mounting bracket lets you hang the fire extinguisher in an accessible spot so it's close at hand if you need it.
Precision tools that perform their task with split-second speed and accuracy are key in jobs where time is of the essence. Take, for example, the nozzle at the end of a firefighting hose. It allows a firefighter to regulate the pressure of the water exiting the hose, no matter how confined or widespread the flames. A fire hose nozzle isn't a simple point-and-shoot device. It enables firefighters to tailor their tactics by firing water in a stream or flush. Production begins with a long aluminum tube. A saw slices off 6-inch pieces called blanks. Just one tube makes about 46 blanks. A robotic arm swoops down to transport them to a lathe. Cutting tools form the valve body, which controls the flow of water. Then they rough up the surface, making it easier to grip. They make a ball groove on the outside rim for attaching the hose coupling. Next, they form the interior. Technicians verify the inside shaping with computer imaging software. It's on to the milling process. A computer-guided drill bores several holes for the nozzle and grip attachments. Coolant washes away the metal chips and keeps the drill bit from overheating. The transformation from a blank to valve body is structurally complete. A laser now engraves the flow indication. Workers install rubber O-rings on a mandrel shaped like the valve body interior. The rings keep water from leaking out the side of the nozzle. They position the valve body over the mandrel and blow the rings into place with a blast of air. Automated machines now mate the valve body to the nozzle's handle. A heated mold melts granulated rubber and casts it into ridges at the top of a rubber cylinder. This makes the shaper, the nozzle's adjustable head that switches the water from a wide spray to a narrow stream. Workers snip off any excess rubber, then ensure the rubber is solidly molded. Next, they apply grease to the inside to lubricate the parts and prevent corrosion. 2 more O-rings are inserted to keep water from leaking out under the shaper. Using a specially designed spoon, they scoop up tiny plastic ball bearings and drop them into a groove in the shaper. These allow the shaper to rotate easily. The shaper then goes over a barrel, a metal tube that helps form the stream of water. To attach it, they apply an adhesive to the threads on the shaper's base, then slide the part into place. Workers insert a pair of hard plastic balls into the shaper. These enable the shaper to glide back and forth on the barrel to shape the water stream. Now it's time to build the sub-baffle, the nozzle component that controls water pressure. First, they insert a pressure regulation spring into the baffle body. Then snap on a knob which changes between standard water pressure and low pressure. The whole device slides directly into the barrel. On the other end of the barrel, they screw on the valve body. A rotating wheel simplifies this process. They now affix a pistol-style grip. Finally, the gasket grabber goes in. The steel screen keeps out nozzle clogging debris coming from the hose. With the nozzle assembly now complete, it's time for what they call a damp run. Workers check everything to ensure the nozzle performs its tasks at every twist and turn. From the old-fashioned nozzle to the modern variety that comes in an assortment of flows, pressures, and sizes, the evolution of the fire hose nozzle is undoubtedly a lifesaver. Firefighting used to consist of passing water buckets hand to hand. The first fire hoses of the 1600s were made of leather, but these hoses were heavy, would crack when dry, and often break open under pressure. Modern firefighting began with the lightweight cotton fire hose, lined with rubber to keep the cotton dry and flexible. Fire hoses come in a range of sizes to fulfill a range of functions, from small, lightweight ones for fighting forest fires to large, heavy-duty hoses for industrial fires. Production begins with hundreds of bobbins of polyester yarn, feeding automated looms a floor above. A series of spring rods keeps the yarns under uniform tension. This is essential to create a tight weave. The factory programs each loom to weave specific patterns which incorporate identifier stripes. This is a visual guide to help workers assemble the fire hose later on. This woven fabric will form the fire hose's exterior called the jacket. It's got to weather some nasty conditions, so they soak it in a plastic polymer solution with dye for color. The liquid encapsulates the fibers, making them durable and water resistant. At another station, they mix granules of polyurethane, a form of plastic, with white colorant and adhesive pellets. This mixture is for making the waterproof tubing that forms the inside of the fire hose. When they activate the adhesive in the mixture with heat, this tubing will bond to the hose jacket fabric. The mixer feeds the ingredients to an extruder, which melts the mixture and forms it into a hollow tube. The tube then passes through a basin of cool water to set the plastic. Next, the tube goes to the inspection table, where an automated printer prints code numbers on it for tracking purposes. To assemble the fire hose, they first pull out an outer hose jacket over a 33-yard-long cable. Then, with another cable, they feed a second untreated hose jacket inside the first one. Finally, they attach a cable to the third and innermost layer, the tube, and pull it along the entire length of the double jacket. Once it's all the way through, they trim both ends. The three layers, outer jacket, inner jacket, and tube, are now ready to become one. They begin the fusing process by clamping one end of the assembled hose to a steam nozzle. As the clamp holds the hose steady, the nozzle blasts pressurized steam into the tube. At the same time, it moves backward, pulling out any kinks. The hot steam melts the adhesive in the tube material, and it penetrates the inner jacket around it. Once everything's perfectly straight, they pump in cold air to solidify the adhesive. This permanently bonds the layers. They roll up the finished hose into a coil, controlling the winder with a foot pedal. Then they lay the coiled hose on a table to install the couplings. Those are the components that attach the hose to the water supply on one end and to the spray nozzle on the other. They trim each end and then insert a brass expansion ring and then an aluminum coupling on top. An expansion machine does the rest. They attach the end securely to the machine's protruding bar. Then the bar retracts and expands, pushing the brass ring outward. The force wedges the brass into the aluminum coupling permanently. This company tests every fire hose it produces under high pressure on this table. After marking the type of hose with a stencil and indelible ink, they fill the hose with water. They check for holes and kinks and verify that the couplings stay in place. After the test, they drain the water. They insert a giant sponge to get rid of any water left behind. And now these new hoses are ready for their baptism by fire.